Good morning. I am R. Sivakami, working as an assistant professor in the Department of Information Technology. So today we are going to discuss a maximum flow problem by iterative improvement. So before knowing what is maximum flow problem, we should know what is iterative improvement. Iterative improvement, it is an algorithm design technique which is used for solving optimization problems. So optimization problems are of two types, called maximization problems and minimization problems. In maximization problems, we need to obtain a maximum value for the objective function, whereas in minimization problem we need to obtain the minimum value for an objective function. So for solving both these kinds of problems, we can use iterative improvement. So the general procedure for an iterative improvement method involves, first we have to choose the feasible solution, which is going to be very simple. So feasible solution is a solution which is going to satisfy all the constraints of a given problem, and then we have to improve this feasible solution by repeated applications of some simple step, and this step has to be repeatedly applied several times, and when there is no improvement in the feasible solution, we have to retain the current feasible solution as an optimal solution and the procedure has to be stopped. Here we should know what is the difference between feasible solution and optimal solution. Feasible solution is a solution which satisfies all the constraints of a given problem. For example, if you consider a traveling salesman problem, any tour that visits all vertices of a given graph exactly once is a feasible solution. And then the next one is an optimal solution. So optimal solution is the best feasible solution. If you consider the same traveling salesman problem, a tour which visits all the cities or vertices exactly once with the minimum traveled distance, total traveled distance, is an optimal solution. Next we will discuss what is a maximum flow problem. Actually this maximum flow problem is a problem of maximizing the flow of material through a transportation network. So transportation network may be a communication network or a pipeline system, whatever it may be. So we have to maximize the amount of material which is sent through a transportation network, and in case of this algorithm design technique, this transportation network is represented by means of a connected weighted digraph. So first we should know what is a connected graph. So connected graph is a graph in which each vertex is having a path to all other vertices, and then the next one is weighted. So weighted graph means each edge of a graph is having a weight associated with it. And then the next one is digraph. So digraph, it is otherwise known as directed graph, where each edge is associated with a direction, and here we are having n number of vertices numbered from 1 to n, and out of these n vertices only one vertex is not having any incoming edges, and that vertex is usually chosen as a source vertex. So and then the next one is a sink. So a vertex which does not have any outgoing edges is called a sink, and it is usually given a number n. And then the next term is edge capacity. So with each edge we have to associate one number which indicates the upper bound on the amount of material that can be sent through that particular edge from vertex I to vertex j, and it is usually represented by means of a notation uij. So any graph which satisfies all these properties is called a flow network or simply a network. And then this is an example for a flow network. So if you look at this graph, we are having 6 number of vertices starting from 1 to 6. So out of these 6 vertices, the first vertex 1 does not have any incoming edges, whereas it is having 2 outgoing edges. But since this vertex 1 is not having any incoming edges, it is designated as a source vertex. And if you look at vertex 6, it does not have any outgoing edges, it is having only 2 incoming edges, and hence this vertex 6 has to be chosen as a sink vertex. And here you are having edge capacities. For example, if you look at this number 2, it is associated with this edge 1, 2. So from vertex 1 to vertex 2 we can send a maximum of 2 units of material. Similarly, if you consider this number 5, it is associated with an edge 2, 3. So it means that from vertex 2 to vertex 3 we can send a maximum of 5 units. So that is the interpretation of this flow network. And then next one is we should know what is flow. So flow is actually an assignment of a real number xij to each edge of a given graph by satisfying two conditions called flow conservation requirement and capacity constraint. So here xij, it means that it represents the actual amount of material which is sent from vertex I to vertex j through an edge I comma j. And first let us see what is a flow conservation requirement. So flow conservation requirement means the total amount of material entering an intermediate vertex should be equal to the total amount of material leaving an intermediate vertex. So except your source vertex and sink vertex, for all remaining vertices this condition should be satisfied. So this condition can be written like this. So for any vertex I, sigma xji should be equal to sigma xij. So if you bring the right hand side expression to the left hand side, this equation can be written like this. Sigma xji minus sigma xij is equal to 0. So this is your flow conservation requirement. So let me discuss one example for this. So again consider the same graph. If you look at this, for every edge we are having two numbers. For example, if you consider this first edge from 1 comma 2, you are having a number representation as 2 by 2. It means that the first number represents x value and then the second number represents u value. So once again I repeat, u represents the upper bound on the amount of material, whereas x represents the flow value, that is the amount of material which is currently sent from source to, otherwise from one vertex to another vertex. And similarly, if you look at an edge 1 comma 4, you are having 1 by 3, which means that you can send a maximum of 3 units of material from vertex 1 to vertex 4, whereas currently only 1 unit of material is being sent. So now, for example, consider vertex 2, and here we have to apply this flow conservation requirement for intermediate vertices only. So let us consider vertex 2. So in vertex 2 you are having one incoming edge and you are having two outgoing edges. So incoming edges 1 comma 2. So it is written like this, x12, which is equal to, you are having two outgoing edges 2 comma 5 and 2 comma 3. So it is written as x23 plus x25. So what is the value of x12? It is 2. So it is written here. And then what is the value of x2 comma 3? It is also 1. So it is written here. And then the next one is x2 comma 5. So 2, 5, x between vertices 2 and 5 you are having again 1. So it is written here. So 2 is equal to 2. So the flow conservation requirement is satisfied for vertex 2. Similarly, you can go for checking the same condition for one more vertex. For example, you can consider vertex 3. So this vertex 3 is having two incoming edges 2 comma 3 and 4 comma 3. So their corresponding flow values are 1 comma 1. So they are written like 1 plus 1. And then this vertex 3 is having only one outgoing edge 3 comma 6. So the flow value which appears on that particular edge is 2. So it is written here. So 1 plus 1 is equal to 2, which is equal to this particular 2. So flow conservation requirement has to be satisfied for all intermediate vertices in a given flow network. And then the next condition is capacity constraint. So capacity constraint means the flow value what we are going to assign on edges should lie between 0 and uij. Uij is the upper bound on the amount of material which is sent from vertex I to vertex j. So this condition is written like this. And then if you want to check this condition for this flow network, every first value is less than or equal to the second value. For example, if you consider this 1, 5, 1 is less than 5. If you consider here 2, it is equal to 2. So the first value should be less than or equal to the second value. That is, flow value should lie between 0 and the maximum capacity. So this is your second constraint. And then next we should know what is a flow value. So during intermediate vertices, no extra material can be added, otherwise existing material cannot be lost. So this condition can be written like this for source vertex and sink vertex. So the total amount of material coming from source should be equal to the total amount of material reaching the sink. So source vertex, it is represented by vertex 1 and sink is represented by vertex n. So this condition can be written like this, sigma x1j is equal to sigma xjn. So a sigma x1j represents the total amount of material exiting from source vertex, whereas sigma xjn represents the total amount of material reaching the sink. So Next one is, this is an example for a flow value. So again consider the same graph. Here source is vertex 1 and sink is vertex sink. So what is our condition with respect to flow value? The total amount of material coming from source should be equal to the total amount of material reaching the sink. So from source you are having two outgoing edges. Their flow values are 2 and 1. So it is written. So source is having two outgoing edges. Their corresponding flow values are x12 and x14. Their values are 2 and 1. Whereas from sink, so sink is having two incoming edges 5,6 and 3,6. So they are written here. So on the edge 3,6 you have a flow value 2, and on the edge 5,6 you have a flow value 1. So it is written here 2 plus 1. So 2 plus 1 is equal to 3. So this condition is satisfied. And then now we need to know what is a maximum flow problem. So maximum flow problem, it is a maximization problem where we are going to achieve a maximum flow for a given network. So this maximum flow problem can be written as linear programming problem. So we need to maximize the amount of material coming from source vertex. So amount of material coming from source vertexes, as we have already seen, it is sigma x1j. So we have to maximize this value subject to two conditions. The first condition is flow conservation requirement. So we have already seen that constraint, and this is the corresponding expression sigma xji minus sigma xij is equal to 0. And then the next condition is capacity constraint. So it is written here xij value, that is the flow value should lie between 0 and uij for every edge. So this is the maximum flow problem. And then we have to discuss how we can solve this maximum flow problem by means of iterative improvement method. So as I have already told you, in case of iterative method, we have first step is choosing initial condition, and then second we have to repeatedly apply some simple step to improve the value of an objective function, and that repetition should be continued until we don't have any improvement in the solution. Right? So we have to apply the same procedure to a maximum flow problem. So the first step is we have to start with the zero flow, which means that x value should be given as 0 for all edges. This is the first step. And then the second step is for each iteration we have to try to find out one flow augmenting path. If flow augmenting path is found, correspondingly we have to update flow values on all edges, and this procedure has to be repeated. And when a flow augmenting path is not found, we have to retain the current flow at maximum and the procedure has to be stopped. So this is the outline of the application of iterative improvement method to our given problem, maximum flow problem. Right. So here, while trying to solve this problem by means of an iterative method, we may come across two kinds of edges called forward edge and backward edge. So forward edge means it is an edge which is going from vertex I to vertex j, and you can use this forward edge when the remaining capacity is strictly greater than 0. So how will you calculate remaining capacity? So by means of this expression uij, it is the maximum bound, and then xij, it gives you the current flow value. So for example, assume uij is 5. So maximum you can send 5 units on that edge, and assume xij is 2. It means that currently you are sending only 2 units. So 5 minus 2 becomes 3, which means that you can send 3 more units on that edge. So that gives you your RIG value. So RIG gives you the remaining capacity which can be sent through that particular edge I, j. So this is your forward edge. And then the next one is a backward edge. It is an edge from vertex j to vertex I. So here the flow value xji is greater than 0. So you should have some positive value for xji. And then the next one is how to find out a flow augmenting path. So once you have calculated RIG values and xji values, you need to calculate the minimum between these two values, and that is stored in a variable r. So r is equal to minimum of RIJ and xji values. And then for every forward edge, so that this is for updating the flow values on all edges. So for every forward edge you have to increase the current flow by r units. So what is r? R is calculated here. And then for every backward edge you have to decrease the current flow by r units. So like this you have to update flow values on all edges. And then this is the general algorithm. So first we have to apply breadth first search, which is shortly known as BFS. So we have to traverse the graph by means of BFS, breadth first search. And here each vertex is given two labels, label 1 and that is each vertex is given labels, and first label and second label. So first label indicates the amount of additional flow which can be brought from the source to this particular vertex. So first label gives the amount of additional flow, whereas the second label is having two parts. The first part indicates the vertex from which this particular vertex was reached, and the second part of second label may be either plus or minus. It means that for example, if you have plus, it indicates that this particular vertex is reached by a forward edge, whereas if it is minus, it indicates that this particular edge is reached by a backward edge. And then this is the vertex labeling procedure. So the starting vertex, I mean the source vertex, should be given a label infinity comma dash. So this is the initialization step. And then next, so if you are using forward edge, that is if vertex J is reached from vertex I by means of a forward edge, how will you name that particular vertex? So a vertex is having two labels. So you have to, as I have already told you, you need to calculate the minimum between Rij and the first label of the previous vertex. So that becomes the first label of the current vertex, and since you have reached the vertex by forward edge, the second label should be plus. I indicates the previous vertex. So this is for forward edge condition, and then the next one is for backward edge condition. So if you are having backward edge, you have to use xji value only. So forward edge means you have to use Rij, backward edge means you have to use xji. So if xji is greater than 0, similar to your previous case, you need to calculate the minimum value between the first label of the previous vertex and the xji value, and that becomes the first label of the vertex which is currently being labeled. And since you have reached this vertex by means of a backward edge, you have to use minus symbol. It has to be prefixed with I. So this is the procedure. So after all vertices are labeled, you need to find out augmenting path. So once the sink is labeled, you have to start this procedure. So you have to use the first label of the sink to make updations on the flow values of all edges. So first label of the sink has to be used to update the flow values of all edges. So remember that. And then by following the second labels from source to sink, you have to form an augmenting path, and based on the type of the edge. So forward edge means the current flow has to be increased, whereas the backward edge means the current flow has to be reduced. And then when the sink remains unlabeled, it means that the current that is we have to stop the procedure. So current flow has to be retained as a maximum flow, and the procedure has to be stopped. So this is the general procedure, and we will discuss the time efficiency of this procedure. So number of augmenting paths which are generated by means of this procedure will never exceed nm by 2, and here n represents number of vertices and m represents a number of edges. And if you are using adjacency list to represent this flow network, then it will take O of m time. And if you use that adjacency list representation, then this shortest augmenting path algorithm's time efficiency will be O of nm square. And still we have some other algorithms which can solve this problem on O of n m times. They do not follow iterative improvement method. So if you apply iterative improvement method for solving this maximum flow problem, where the network is represented by means of adjacency list, then its time efficiency will be O of nm square. So if you have any doubts in this, you can go through these references. Okay, now let us discuss one example problem for this case. So consider this network. If you look at this network, we are having 6 edges starting from 1 to 6. So out of these 6 vertices, vertex 1 does not have any incoming edges. It is having only outgoing edges, and hence this vertex 1 should be designated as a source vertex. So this is your source. And similarly, if you consider vertex 6, it does not have any outgoing edges, and hence it should be chosen as a sink vertex. So this is your sink. So now we are going to apply iterative improvement method for solving this problem. So the first step is initialization step, where we have to give 0 to flow values of all edges. So these are the edges we are having here. So all edges should be given a flow value of 0. So 0 by 5, 0 by 6, 0 by 7, 0 by 4, 0 by 4, 0 by 2, 0 by 8. So if you consider this, for example 0 by 5, it means that through this edge you can send a maximum of 5 units, but currently we have only 0 flow through this edge. Similarly for other edges also, and then we have to traverse this network by means of a breadth first search starting from source vertex. So this is your source vertex. From the source vertex you can go to vertex 2 through this edge, and also you can go to vertex 3 through this edge. So from 1 you can go to 2 and 3. From vertex 1 you can go to 2 and 3. So first consider vertex 2, and here we have to calculate the remaining capacity. This vertex 2 can be reached from vertex 1 through forward edge if and only if the remaining capacity is greater than 0. So calculate the remaining capacity. Maximum capacity is 5, current flow is 0, so the remaining capacity is 5 minus 0, which is 5. So 5 is greater than 0, and hence we can reach this vertex 2 from vertex 1 by a forward edge. So the remaining capacity is 5. So before that we have to give a label to source vertex. So source vertex should be given a label infinity comma dash. So write that infinity comma dash. The label of vertex 1 is infinity comma dash, and then now we have to label vertex 2. So here we have already calculated the remaining capacity, which is 5. So we need to find out the minimum between 5 and the first label of the previous vertex. It is infinity. So minimum between 5 and infinity is 5. So you have to write 5 here first, and then vertex 1, that is from vertex 1 we are reaching vertex 2 by a forward edge. So the second label of this vertex 2 should be 1 plus. So here this 1 indicates that vertex 2 is reached from vertex 1, and this plus indicates that by means of a forward edge we have reached this vertex 2. So from vertex 1 we have reached vertex 2, and then from vertex 1 we can reach vertex 3 also, and the similar procedure has to be applied. So calculate the remaining capacity. It is 6, that is 6 minus 0 becomes 6. So find out the minimum between 6 and infinity. So it is obviously 6. So the first label of vertex 3 is 6, and then since vertex 3 is reached from vertex 1 you have to write 1, and since it is a forward edge it has to be written as 1 plus. So the label of 3 is 6 comma 1 plus. So from vertex 1 we have labeled vertex 2 and vertex 3. So next go to vertex 2. So from vertex 2 you can go to vertex 4 and vertex 5. So from vertex 2 you can go to vertex 4 and 5. So again calculate the remaining capacity. Here it is 4 minus 0, 4. It is greater than 0. So minimum between 4 and 5, that is the first label of the previous vertex. Minimum between 4 and 5 is 4. So you have to write 4, and this 4 is reached from vertex 2 through a forward edge. So you have to write 2 plus. And the next one is from vertex 2 you have to label vertex 5. So here the remaining capacity is 2, it is greater than 0. Minimum between 2 and 5 is 2. So you have to write 2 comma, since 5 is reached from 2 by a forward edge you have to write 2 plus. And the next come to what? From 1 we have named vertices 2 and 3. From 2 we have named vertices 4 and 5. So next come back to 3. From 3 we can go to only 4, but 4 is already labeled. So go to vertex 4 and 5. And then next come to vertex 4. So from 4 you can go to vertex 6. Here the remaining capacity is 4, which is greater than 0. So minimum between 4 and 4, it is 4 only. So you can write 4, and since 6 is reached from vertex 4 by means of a forward edge, you have to write 4 plus. So the sink is labeled. So after labeling all vertices, and especially after the sink is labeled, we have to find out a flow augmenting path. So in the process of identifying the flow augmenting path, you have to use the first label of the sink vertex for updating the flow values of all applicable edges. So you have to use this value for only, and then by following the second labels from source to sink. Now from vertex 4 we have to make a traverse. So from vertex 4 you can reach vertex 6 and this is the edge. Here the remaining capacity is 4. So minimum between 4 and this 4 is actually 4. So you have to write 4 here. And then since vertex 6 is reached from vertex 4 by means of a forward edge, it has to be given a second label as 4 plus. So once the sink is labeled, we have to identify the flow augmenting path. So in the process of identifying the flow augmenting path, the first label of a sink has to be used to update the flow values of all applicable edges. And then here we are having second label, and to find the flow augmenting path we have to follow the second labels from sink vertex to source vertex. This is the procedure. So we will start with the sink vertex. The second label of the sink vertex is 4 plus. So from 6 we have to go to vertex 4, and since here we are having plus, it indicates that this flow value has to be increased. So this flow value 0 has to be increased by this 4. So this 0 becomes 4. Now this becomes your current vertex, and here the second label is 2 plus. That means from 4 you have to go to vertex 2, and since you have plus here, it indicates that the corresponding flow value has to be increased. So the flow value is 0, and this 0 should be added with this first label, so it becomes 4. Now this becomes your current vertex. Here the second label is 1 plus. So from 2 you have to go to vertex 1, and here the current flow value is 0. It has to be increased because here you have a plus symbol. So this 0 should be increased by 4. So this becomes your new flow value. So now we have updated some flow values on some edges. So redraw the graph again. So it will become, you are having So redraw the graph. First write the flow values of updated edges. So the updated edges are 4 by 4. Here you have 4 by 4, and this is 4 by 5. So these are the updated edges, and for the remaining edges also write the values, previous values. So this edge is 0 by 6, and this one is 0 by 7. And from vertex 2 to 5 you are having 0 by 2, and from vertex 5 to 6 you have 0 by 8. So this is your next iteration. So as usual we have to give a label to source vertex infinity comma dash. So it is infinity comma dash, and now we have to apply BFS traversal. So from 1 you can go to 2, and also from 1 you can go to 3. So here calculate the remaining capacity. So current flow is 4 and maximum flow is 5. So remaining capacity is 1. 5 minus 4 is 1. So this 1 is greater than 0. So calculate a minimum between 1 and infinity. It is 1. So the first label of vertex 2 becomes 1, and since this vertex 2 is reached from vertex 1 by a forward edge, you have to write 1 plus. So this is the label of vertex 2, and then from vertex 1 you can reach vertex 3. And what is the remaining capacity here? It is 6. So minimum between 6 and infinity is 6. So you have to write 6 here, and then since 3 is reached from vertex 1 by a forward edge, you have to write 1 plus. So from vertex 1 you have named vertices 2 and 3. Now start from vertex 2. So from vertex 2 you can come to vertex 4 and vertex 5. So first consider vertex 4. Calculate its remaining capacity. It is 4 minus 4, which is equal to 0. But what we require is a positive remaining capacity. That is, it should be strictly greater than 0. But here it is equal to 0. So you cannot use forward edge to reach 4 from 2. So leave this 4 now. So from 2 you can go to 5, and here the remaining capacity is 2. 2 minus 0 is 2. So minimum between 2 and 1 is 1. So you have to write 1, and since 5 is reached from 2, you have to write 2 plus. So from vertex 2 you have named vertex 3, and then now come to vertex 3. So from 3 you can go to vertex 4. So calculate its remaining capacity. It is 7 minus 0, 7. So minimum between 7 and 6 is 6. So you have to write 6. And since 4 is reached from 3 by a forward edge, you have to write 3 plus. So from 4 you have written that is the label of 4 is 6 comma 3 plus, and then next you have to come to vertex 5. So from vertex 5 you can reach vertex 6. Its remaining capacity is 8. Minimum between 8 and 1 is 1. So you have to write 1, and this vertex 6 is reached from vertex 5. So you have to write 5 plus. So once the sink is labeled, you have to find out the flow augmenting path. So this value has to be used to update the flow values of all edges, and then this second label has to be followed from sink vertex to source vertex. So its second label is 5 plus. So you have to go to vertex 5. Here the flow value is 0. This 0 should be increased by 1. So this 0 becomes 1. Now this becomes your current vertex. So here the second label is 2 plus. So you have to go to vertex 2. And here the flow value is 0. It has to be increased by this 1. So the 0 becomes 1. And then the second label of this 2 is 1 plus. So from 2 you have to go to vertex 1. And here the flow value is 4. 4 has to be increased by 1. So 4 plus this 1 becomes 5. So here it is 5. So you have reached source vertex, and this procedure has to be stopped. So now redraw the graph again with updated flow values. So you can write so you are having 6 vertices. So write the flow values also. So write the updated flow values between vertices 1 and 2, 5 by 5, and from 2 to 5 it is 1 by 2, and from 5 to 6 1 by 8, and from 4 to 6 4 by 4, from 2 to 4 again it is 4 by 4, from 1 to 3 it is 0 by 6, and then from 3 to 4 it is 0 by 7. So again vertex labeling has to be done. So it is so give a label to vertex 1, that is the source vertex, as infinity minus. So starting from this source vertex we have to traverse the remaining vertices by means of a breadth first search, BFS. So from 1 you can go to vertex 2, but here if you calculate the remaining capacity, 5 minus 5 becomes 0. So you cannot reach this vertex 2 by a forward edge. Anyway, from 1 you can go to 3. So calculate its remaining capacity. It is 6 minus 0. 6 minus 0 is 6. So 6 is greater than 0. So calculate the minimum between 6 and infinity. So it becomes 6. And since 3 is reached from vertex 1, you have to write 1 plus. So now what we have done is from vertex 1 we have reached vertex 3. So now we are in vertex 3. So from vertex 3 check whether we can go to vertex 4. So calculate its remaining capacity. It is 7 minus 0. 7 minus 0 is 7. 7 is greater than 0. So find out the minimum between 7 and 6. So it is 6. So I have to write 6 here. And since 4 is reached from 3 by means of a forward edge, you have to write 3 plus. So from 3 you have reached 4. Now your current vertex is 4. From this 4 you are having only one outgoing edge, that means you can reach vertex 6 only. So here check what is the remaining capacity. So remaining capacity is 4 minus 4. 4 minus 4 is 0. Since it is not greater than 0, you cannot reach 6 from this 4 by means of a forward edge. So again come back to vertex 1. So from 1 you cannot reach vertex 2. Anyway here you have to label vertex 2. Since 5 is not named, you cannot name 2 from vertex 5. So check this vertex 4. So vertex 4 is given a label 6, 3 plus. So the current vertex is 4. So from vertex 4 we can go to vertex 6. So you can write like this. So calculate its remaining capacity. It is 8 minus 4. It is 4. 4 is greater than 0. So find out the minimum between 4 and 6. It is 4. So you have to write 4. and since vertex 6 is reached from vertex 4, you have to write 4 plus. So 6 is the final vertex. From this you don't have any outgoing edges. So now look at the remaining vertices. So here you are having vertex 2 and vertex 5 which are not labeled. So now we have to label this vertex 2. So to label this vertex 2, you cannot use vertex 1 because its remaining capacity is 0. So check this vertex 4. So here you can apply a backward edge. So to apply a backward edge, the condition is xji value should be greater than 0. So corresponding to this edge, the xji value is 4. 4 is greater than 0 and hence the condition is satisfied. So find out the minimum between this 4 and previous label's first vertex. It is 4. So you can write 4, and since this vertex 2 is reached from vertex 4 by means of a backward edge, you have to write 4 minus. So the label of vertex 2 is 4 comma 4 minus. Now from this vertex 2 you can go to vertex 5. So the remaining capacity here is 2 minus 1, 1. Minimum between 1 and 4 is 1. So you have to use the least value 1, and this 5 is reached from vertex 2 by means of a forward edge. So you have to write 2 plus. Now we have labeled all these vertices. So starting from sink to source, we have to find out an augmenting path by following this second label, and the first label of sink vertex has to be used to update the corresponding edges. The second label of vertex 6 is 4 plus. So from 6 you have to go to 4, and here the flow value is 4. It is the previous value. It has to be increased by this 4. So 4 plus 4 becomes 8. So this 4 has been changed to 8. Now this is your current vertex, and here the second label is 3 plus. So from 4 you have to go to vertex 3, and since you have plus here, the flow value has to be increased by the first label of the sink vertex. So here the flow value is 0. It has to be added with this 4. So the 0 becomes 4. Now this is your current vertex, and its second label is 1 plus. So from vertex 3 you have to go to vertex 1. Its flow value is 0. This 0 has to be added with this 4. So this 0 becomes 4. So now we have reached vertex 1. So this iteration has to be stopped here. Now redraw the network again. So you are having 6 edges, 1, 2, 3, 4, 5, 6. So make entries for edges. So from 1 to 2 you are having 5 by 5. From 2 to 5 you have 1 by 2. 5 to 6 is 1 by 4. 4 to 6, 8 by 8. 2 to 4 is 4 by 4. And 3 to 4 is 4 by 7. And 1 to 3 is 4 by 6. So now the same procedure has to be repeated. So label the source vertex by infinity comma dash. So from vertex 1 you can go to vertex 2, but check this remaining capacity. It is 5 minus 5, which is equal to 0. Our condition is the flow value remaining capacity should be greater than 0, whereas here it is not the case. So you cannot use this edge. Anyway, from 1 you can go to 3 by means of a forward edge. Since this remaining capacity 6 minus 4 is equal to 2 is greater than 0. So from 1 you can go to vertex 3. So remaining capacity is 2. Minimum between 2 and infinity is 2. So the label of vertex 3 is 2 comma 1 plus, since you are using a forward edge. So from vertex 3 you can go to vertex 4. So check the remaining capacity. It is 7 minus 4, 3. 3 is greater than 0. Minimum between 3 and 2 is 2. So you can write 2 comma 3 plus. So from 4 you can go to check whether you can reach vertex 6. So the remaining capacity is 0. 8 minus 8 is 0. It is not greater than 0, and hence you cannot use this forward edge. So 5 also cannot be labeled by this time. So go to vertex 2. So 2 cannot be labeled from vertex 1 by a forward edge. So check whether you can reach vertex 2 from 4 by a backward edge. So to use a backward edge, the condition is xji should be greater than 0. Xji value here is 4. 4 is greater than 0. So you can use that path. So minimum between 4 and 2 is 2. So you have to write 2, 4 minus. Here minus indicates that this vertex 2 is reached from vertex 4 by means of a backward edge, and from vertex 2 check whether you can reach vertex 5. Here the remaining capacity is 1 greater than 0, minimum between 1 and 2 is 1, so you have to use 1, and 5 is reached from vertex 2 by a forward edge, so you have to write 2 plus, and then from vertex 5 you can go to vertex 6. The remaining capacity is 3, minimum between 3 and 1 is 1, so you have to use 1, 5 plus, because vertex 6 is reached from vertex 5 by means of a forward edge. We have given 5 plus as a second label for the sink vertex. So now we have given labels to all vertices. So starting from sink, by following the second path we have to identify the flow augmenting path. So for making updations on flow values you have to use this number 1, that is the first label of the sink vertex. So the second label of sink vertex is 5 plus, so you have to go here, and here the flow value is 1, that one has to be increased by this 1, so it becomes 2. So this is your current vertex, and here the second label is 2 plus, so you have to use this edge, and here the flow value is 1, 1 has to be increased by this 1, so it becomes 2. And here the second label is 4 minus, so you have to come here, and this edge has to be updated, and since here you are having minus, the flow value has to be decreased, so this 4 has to be decreased by this 1, so 4 minus 1 becomes 3, and this becomes your current vertex, and here the second label is 3 plus, so you have to use this edge, and here the flow value is 4, it has to be increased by 1 since you are having plus here, and this 4 becomes 5 now, and the second label of vertex 3 is 1 plus, so you have to go to this vertex through this path, and here the edges edge value, flow value is 4, so this 4 has to be increased by this 1, so this 4 becomes 5 now, 4 plus 1 becomes 5, and you have reached your source vertex, so you have to stop. Now redraw the graph again. So you are having 6 vertices, 1, 2, 3, 4, 5, 6. So write the labels, that is write the edge values. 5 by 5, it becomes 2 by 2, and this one is 2 by 4, 8 by 8, 5 by 7, 5 by 6, 3 by 4. So now again we have to go for the iteration. So as usual, label source vertex as infinity dash. So from 1 check whether you can reach 2. You cannot reach because the remaining capacity is 0. From 1 you can go to vertex 3 because the remaining capacity 1, which is non-zero. So minimum between 1 and infinity is 1. So you have to write 1. And since this 3 is reached from vertex 1, you have to write 1 plus. And then from 3 you can reach 4 because the remaining capacity is 2, which is non-zero. Minimum between 2 and 1 is 1. So you have to write 1, 3 plus. And then from vertex 4 you cannot go to vertex 6 because the remaining capacity is 0. So come to vertex 2. So 2 cannot be reached from 1, we have already seen that. So you can use this backward edge. Here the xji value is 3, 3 is greater than 0, minimum between 3 and 1 is 1. So you can write 1, 4 minus. Here minus indicates that this vertex 2 is reached from vertex 4 by a backward edge. And then next come to vertex 5. So from 5 you cannot, that is from 2 you cannot reach 5 because the remaining capacity is equal to 0. Similarly 6 cannot be labeled because here the remaining capacity is 0, and since 5 is not labeled you cannot label 6 also. So here our iteration stops because we cannot label all these vertices. So we have to stop this here itself. So redraw the graph. We are having vertices 1, 2, 3, 4, 5, 6. So write the flow values. 5, 5, it is 2, 2, it is 2 by 4, 3 by 4, 5 by 6, 5 by 7 and it is 8 by 8. So this is your source and this is sink. So consider your source vertex. In source you are having two outgoing edges, which is 1, 2 and 1, 3. So write their flow values. They become x12 and x13. x12 value is 5. So you have to write 5 plus x13 value is also 5. It is equal to 10. And consider the sink vertex. It is sink. In sink you are having two incoming edges. So they have to be written as x46 from 4 to 6, and then from 5 to 6 you have x56. So x46 is 8 and x56 is 2. So you have to write 2, which is equal to 10. So from source you are sending 10 units of material, and at the sink you are receiving the same 10 units of material. So your condition is satisfied. So the solution is maximum flow is 10. So we have solved the problem. So for the given problem we have find out the solution is 10 units. So I will give you summary. First we have to initialize 0 values to all flow values of all edges, and then we have to apply BFS for vertex labeling. And once the sink is labeled, we have to use the first label of the sink vertex for updating flow values of corresponding edges, and by following the second label from sink to source we have to identify the flow augmenting path. As long as flow augmenting path is found, we have to repeat this procedure. When the flow augmenting path is not found, the current flow should be written as a maximum flow. That's it.